after 2 years of intensive research, we are now in position to showcase some of the results that have been achieved in the project. I'm very excited to see those demonstrations, which are very complementary in the way they address different kind of ethical issues we have in automated driving.
Personally, I'm deeply convinced that progress in automotive driving is directly connected to virtual validation. Why is this the case? Because there are so many safety-critical scenarios and edge cases you cannot test in reality, so you have to use simulation. And there's one big issue, especially in urban scenarios, so you cannot predict the movement of the pedestrian. And with our approach, it is possible to connect a simulation tool directly with a real person, which is put in the scenery, and therefore you are able to provide realistic trajectories. And this will push automated driving and the virtual validation a step forward.
In the context of the project, as virtual vehicle, we integrate virtual reality with Carla driving simulator in order to collect safety-critical scenario-specific data to provide safe environments for the pedestrians. With this framework that we develop, we place real human agents with virtual reality as pedestrians in the simulation, and we collect their trajectory data. With the collected trajectory data, the developed models in the project, developed AI models in the project can be tested accordingly.
So in our case, the demo shows current state of our open source implementation of the simple ADAS solution for the project. It consists of 3 simple functions. The first one is line keeping, the second one is emergency braking, and the third one is speed keeping. In our presentation, you can see the comparison of driving manually without these functions enabled. Then you can see several variations of driving automatically with these functions, and you can see also some edge cases when the pedestrians are already almost out of range of the sensors.
In our demo, we demonstrate a simple ADAS algorithm which can be found in current modern vehicles. It's of course simplified version, but it's clearly seen its advantages, disadvantages and limitations. And we would like to compare this algorithm with the same algorithm but enhanced by the AI models, predicting the movement of the vulnerable road users based on the KPIs. And such algorithms should help to build the trust of the users and also make the drive much more safer and smoother.
Our demo is about Pollux, our digital twin that we developed at Acodes. So one thing with the existing simulators today, like Carla, is that all the maps they rely on are hands-made. And so this is useful in most cases, but not really realistic. And you can't always find the right spot you want to test your simulation on. So our aim with Pollux is to be able to reproduce any street from an existing city in real life, including the buildings, the road network and the urban furniture, and be able to perform simulations there, and only using open source data like OpenStreetMaps. On top of that, we integrated many different components like a ROS bridge to which you can connect any AI model you want. And the final goal with this is to be able to make it a seamless experience for OEMs, for instance, who want to test their systems, but also for researchers like us at AI4CCAM.
What we demonstrated today was our digital twin called Pollux, in which we try to recreate reality inside a simulated environment. The simulated environment is, in essence, an AI playground. And this AI playground, in my opinion, can solve 2 of the major problems that we have in the field of automated mobility. One of them is repeatability, so you can run different scenarios that affect the environment and that affect the vehicle as many times as possible and hope to get the same results every time, or try to essentially repeat the same thing over and over again while changing the parameters in very small ways. The second one is safety, which is you can clearly use and try out as many AI models as possible within this environment, within this AI playground, without putting any vulnerable road user or any other shared space user, like a bicycle or any other car, in danger. What this allows us to do as a community as a whole is try to expand our horizons and not be limited specifically to the real environment, while gathering data from the real environment and translating it into a simulated environment to be able to test out many of our different theories and many of our different algorithms.
So something we know that CIV need to understand the human world and understand the human behavior and act accordingly to that. But in the same time, human is naturally adapt themselves to the environment. So for example, when you think that the car seen you, you will act differently than when you think that the car didn't see you. And so the challenge is to find a good way to give to the CIV a way to communicate with pedestrians and the information that they seen you. So yeah, a simple way to address this problem is to use green or red light or sound, but there is some limitation with this if you want to communicate with many pedestrians at the same time. So we choose another approach, a biomimetic ones, so to try to mimic the eye gaze, to try to communicate this information with pedestrians. So in our demo, we try to address this and focus on many pedestrians at the same time. That is not done previously, because all the time previously was just focus on one pedestrian at the same time. So we will try to achieve this.
So I believe that there are two major impacts of our demonstration. First, the demonstration demonstrates our technology where we integrate virtual reality with the Carla simulator. Simulators are very important for automated vehicle testing, but how they have been used till now is people have put the automated vehicles into these simulators to recreate and test their behaviors in scenarios that they cannot do in real life. But what the integration with virtual reality enables us to do is put not just the automated vehicle, but also pedestrians in the scenario to see how they perceive this automated vehicle behavior. And that brings me to my second impact, which is that with this demonstration, we look at the perception of humans, how it changes when the people are given a feedback about if the vehicle has seen, the automated vehicle has seen them or not. So from our work in neuroscience, we work a lot in the neuroscience of human-machine interaction. We know that humans the comfort of humans are not determined not by the behavior of the machines, or not just by the behavior of the machines, but also by the fact by how they perceive these behaviors. So that means that it's very important for automated vehicle when it perceives a human, when it knows that the human is there. It's very important for it to share this perception with the pedestrian. So here with Enzo, we try to use a biomimetic technique to do this, and we are examining how this can be useful for automated vehicles. And for this reason, this is something that is very rarely investigated in the automated vehicle community, and we believe that this is one of the few experiments for this, and that's why it will be very useful for the community.
Autonomous mobility is a very important topic for the European Commission, and we are with these demos we are contributing to the CCAM ecosystem in the sense that we address a very specific issue related to trustworthy AI and ethical issues in automated driving.